Welcome, microcomputer applications specialist. We're going to talk about, we've talked about analog to digital converters. Now we're going to talk about digital to analog converters, and one particular converter we're going to explain. You can get integrated circuits just like with analog to digital converters. You can get integrated circuits that'll perform the digital to analog conversion. That is, you give it a number and out comes a voltage. That's also possible with a passive resistor network called an R2R ladder. And I have such a part right here. I'll put a data sheet in our Blackboard site. And what I have here is 8 bits, P0 through P7 from our basic stamp, ground, and an output pin. And we will put an 8-bit number out on P0 through P7, or I guess, if you're counting the most significant bit first, it's P0 down. It's P7 down to P0. And we'll get an output here. We're referencing to ground, and we'll read the output on our meter. And so I'm going to go now. Of course, I run P basic over on the Windows side of this, so I'm going to slide over here, and we have a program here. Let's take a look at our code first. We have the usual green code up here, and this isn't even right. This is we're outputting a byte to an 8-bit R2R ladder digital to analog converter. And so we have a byte variable. We set it equal to 0 to start with, and since we're going to output 8 bits at one time, we can refer to the output port, P7 down to P0. We can refer to it as out L for low. P15 down to P8 is called out H. And so what we're going to do is we're going to first of all, we're going to set this keyword variable here, DIRL. It's the direction register for the low byte, and we're going to set it to all ones, which is 255 in decimal. So P7 down to P0 are all output lines now. And then we're going to repeatedly do this loop where we ask the user to enter a number from 0 to 255, and here's the debug in. Dec3 means give me a 3-digit number. We then print a carriage return, and we take that number, which is in X, and we assign it to out L, which is our output port, P7 down to P0. So we'll run this like so, and our first number we can put in, if we put in 255, you will see, let me go back here, you will see we are at 4.97 volts. And if I were to take my calculator, and let's say I did, now with 8 bits we can have 256 values. And let's see if this will. A little better. So if I take 5 volts, I guess you can't see that. I'm sorry. 5 volts times the largest number we can output is 255, and divide it by 256, I get 4.98 volts essentially. And when I put out 255 here, that was what I read in. If you remember here, we drove out a 255, and instead of getting 4.98, I got 4.97, and that's actually, I'm not too worried about that difference. Now, if we wanted to put out a value that was about half of 255, we know that 128 is half of 256. That isn't what I wanted. Let me try 128. There we go. So 128 is about halfway to 255. If I come back here, you can see I'm very close to 2.5 volts. Just as I was very close to 5 volts when I put out 255. And if I put out 64, that's half again that voltage. So I come over here and I say 64. And I come back over here, and now I got about 1.25 volts, very close to 1.25 volts. If I go half again, I should get something like 0.6, 0.625, I think is what we should get, 0.625. Of course, it'll be a little bit below that. So I come over here and I put in 32. And I come back over here and I get 0.624, pretty close. And if I put in half of that, I'll get, 0.312 or something like that. So if I put in a 16 here, I've gone 128, 64, 32, 16. I put in 16. I'm down there around 312, 0.312, 312 millivolts. And we can keep going. Let's do 8. And half of 312 should be 0.156. And there we are. We have 156 point something millivolts. And it'll get pretty flaky here. We go to 4. Instead of 156, we should get, I don't know, maybe 78, 79 millivolts now. And so there we go, 78.5 millivolts. So that's working pretty well. So that's great. We can output a value, and this could be a value that controls something in a process. The other way we can do this is we can take and I'm gonna save this program because I didn't do that before. And I guess we'll save it here and we'll call it now. Got another program here with a similar name. One is EET 260 under DAC under 0001.bs2. This one's the same thing, but it's 0002. So let me save this one and give you a little explanation of what it is I'm trying to do. So in the code in this one, we have a variable. We set it equal to 1, or heck, I guess we can start it out at 0. All right. We make the output port. We'll make P7 down to P0 all outputs. And then what we're going to do is we don't need that line. It would just take up time. So we're going to set x equal to x plus 1, and we're going to output x. In fact, maybe the better way to do this would be to output X first, then add 1 to X. When we get up to 255 and we add 1, it'll go to 256, but our variable is a byte, which only can hold 8 bits, and 256 becomes 8 zeros. So this will just repeatedly climb up to 255 and then drop to 0, and climb up to 255 and drop to 0. And so we can run this program, and then let me go back over here, and I've hooked my oscilloscope up to the output of this thing, and you can see here that the waveform is climbing from 0 almost to 5 volts. It's just a whisker short, as we know. It's like 4.9 something volts, and it's just repeatedly doing that. So there's a ramp waveform that's made by a digital analog converter. By doing this, you can get an idea of what arbitrary waveform generation is all about. You just shove numbers in the right sequence out to a analog to digital converter. Out to a digital to analog converter, and you can get an analog voltage. Now, it's a little bit difficult for you to see. Maybe I can do something here. And do a little better triggering job here. Okay. Now our triggering is a little more stable. You can see that these things are steps. If I were to, you can, it's just not. I know how I can make it look more like steps. I can go back and change the program. So let me leave the camera right there. We'll go back to what we had before. 1 volt. There we go. And instead of, what I'm going to do is, instead of adding 1, I will add 8 each time. And now we'll put that out there. And cycling through them. But now you can see the steps a little better. And if I added 16, that would make it even more prominent. And you can see the steps. You can see the steps over here as it goes up. So you couldn't see them before because with 8 bits the resolution was so fine that, and the camera blurred the bright face of the scope over. But essentially we can create voltages. Now if we took this and put it through a low pass filter, all these quick changes would get smoothed out. And if we did it correctly, we'd come back and wind up with a ramp voltage like that. But let's go back to doing the full. Instead of adding 16, we'll add 1. Oops, sorry. And we'll load that. And now you can see that waveform, and maybe you can imagine that these are all, there's 255 little steps between here. Then when you add 1 to 255, it becomes 256, which is 1 and 8 zeros. We don't even see the 1, we just see the 8 zeros, and so we drop back to 8. We drop back to 8 zeros, which is 0 volts. And there's other things we could do. If we wanted the waveform to go the other direction, we could just subtract 1 instead of adding 1. Let's see how this does. And now we go over here and see what happens is we eventually get to 255, and then we subtract down, and we have a ramp waveform that's sloping down instead, in time instead of sloping up. So just trying to show the idea of a digital to analog converter. And analog to digital and digital to analog are very critical components in a signal processing scheme that involves any digital logic or microcontrollers or anything. And if you're looking at waveforms for audio, then you want those digital to analog converters to be very high fidelity. If you're looking at sensors and systems, you may want the digital to analog converters also to be very high fidelity and to be tested and characterized, so that you can make very fine measurements and control things at a fine resolution. So anyway, I will post the data sheet for I'll post our programs here, and I'll post the data sheet for this let's see if I can get this back to where we'd like to have it. Turn that off. The data sheet for this R2R resistive ladder network. Let me see if I can pull one out of here and show it to you. It's a bunch of resistors in the R2R ladder format, but they're on a ceramic substrate with pins coming off it. So now these are obviously, this is a through-hole component, and let's see if I don't know if you can see it any better here. That's what it looks like. There's a little bit of writing on there. There is a dot right there, so you can tell pin 1, and then basically pin 1 is a ground. You have your 8 data pins, and so there's a ground. Pins 1 through 9 are your 8 data pins, and pin 10 is the output. You can see that wired up here. Here's this black wire is the ground. Those 8 wires are your data outputs, and then this white wire is your output, and it's going to the oscilloscope. And it's very common to follow this with a voltage follower, or what some people would call a unity gain buffer. I don't know what some people would call it. Any person would call it that. It's a good name for it. Voltage follower is kind of an old-fashioned name. So that's one type of digital to analog converter. But basically, a digital to analog converter is a box where you put in a vector of signals that, for example, maybe the signals go either 0 or 5 volts, that kind of thing. And out the other side comes a voltage that is proportionally somewhere between a minimum voltage and a maximum voltage. And as you can imagine, as the precision and quality of these digital to analog converters and the analog to digital converters are refined, these things can get amazing performance, and you can do some amazing things with them. So until next time, we say adieu, and take it easy, and we'll talk to you soon. Okie doke, bye.